hope you guys can see my screen. So I'm talking about the whole progress of feature extracting for chemical machine learning. So Damien and I, we worked on that for quite a bit now. And at the beginning, we had a lot of problems in the communication about it. So we thought it would be a nice topic just to talk a little bit about it, because there are some problems in it which you need to know, and you can't really know them just by starting in the whole field. I'm pretty sure in this call there are a lot of people which know that topic much better than we do, but at least we worked on that the last 4 months. And yeah, so just a short overview. I want to start about what is a feature in chemistry at all, then a little bit more about how to extract them. Then we're going more in the machine learning field and about the representation of features. And then we'll going into what are common issues, a little bit about a case study. And then we're going to what is what does mean size in features. So first of all, what is a feature? Yeah, you can see a feature as something you can measure or which is characteristic for observed system. And it's like the essential input for a machine learning system. So that's basically what a feature is. But what is a feature for a molecule? So I just have here like a easy 2D molecule. And yeah, that's we can get the chemical formula, the molecular mass, and stuff like this out of it. Also, we can get the structural formula and charges. But a much better representation would be a 3D presentation. So, for example, from a force field calculation or a quantum mechanical calculation or some kind of semi-empirical calculation. By this, we, for example, get atom coordinates or charge distributions, angles, torsions, and also more complex chirality. So that's all very easy to understandable features. But where do I can get those features from? So reactions conditions and stuff like this, I can easily extract from known databases like Reaxys, SciFinder. That's already common to do in organic chemistry. So if you want to do some kind of reaction, you go onto SciFinder and just check what are the conditions for these reactions, and there you basically do it. So that's basically the same. But how can I get more molecular features? So those are often referred as descriptors, and there are certain libraries for those. For example, RDKit, which is an open source project, or also projects which you need to pay for example, Autodesk. Or there are a little bit more complex ways, for example, to use cclib to extract features. I will talk more about that later. And also, which is pretty common, to use self-written descriptors. So a lot of members of the CCARs are doing that. So first of all, I want to focus on RDKit and Mordred. So RDKit is much more than just a descriptor library. Most people know that. It's a Python and C++ based tool which you can use to treat molecules in Python or in C++. But for the feature extraction, we basically can take a SMILES or any kind of input file and, for example, optimize in a force field, or we don't even need to optimize it. We can just extract some features out of it. So RDKit offers more than 100 different descriptors. Even more descriptors you can extract from Mordred, which is RDKit based. It's around 1,825 descriptors at the moment. So what kind of features can I extract from RDKit? So RDKit difference between 2D and 3D descriptors. The 2D descriptors are mainly stuff like number of rings, number of double bonds, but also a little bit more complex ones. For example, the BCUT2D, that's like a list of different things. For example, gas-like charges are in there, and also a lot of other features. So I get either integers or lists of floats. Also, I can get 3D descriptors. Therefore, I need, for example, do a force field optimization. For example, a sphericity here. That's like the difference from an actual sphere, or the radius of gyration, which is the difference for masses. So how the mass is distributed on the sphere of the molecule. So then something we are doing at the moment a lot, or we're at least trying to do it, is to use CClib. That's just an example for extracting features out of computational chemistry calculations. So CClib supports, for example, different packages. On one hand, we have, for example, QChem, Gaussian, but also older things like turbomole. And we can extract about 70 attributes out of those calculations. Not every attribute is like supported from every package, but that's not like a big deal. Everything can be looked up on the website. And yeah, the most attributes are supported by Gaussian. I also have here some examples. So there's nearly all our 3D descriptors, because we obviously need to do quantum mechanical calculations. So we can, for example, get the atom coordinates, we can get the free energy, we can get the MO coefficients, or also like the vibrations for IR spectra. The problem here is that those are all have different types. So the atom coordinates are a dictionary of arrays. Free energies of floats. And yeah, that's like that's also a large problem for a lot of machine learning systems, that we need like similar types of data. And yeah, so now Damien can talk a little bit more about the machine learning part of it, and how those problems can maybe be solved, and what problems also from machine learning side are occurring when you're working on chemical data.
Yeah, thanks, Niels. Yeah, so like Niels was saying, once, the first step in the process really is to kind of extract and get some chemical features. And then typically the next step would be to take those features and incorporate them into some type of a machine learning model. So just by way of kind of just to motivate things a bit, we show here kind of a chemical formula that's expressed in as a string. So what we find sometimes is that how we decide to actually express the chemical information can affect the type of machine learning model that we end up working with. So for example, last week, there was a presentation that talked about different string representations. There were smart, some of the different representations could be smarts, it could be smiles, it could be deep smiles, or even selfies. And so for probably, the first three of those, and this is not always the way it has to be, but certainly one approach would be to use sequence-based models, which typically would be kind of recurrent neural networks, LSTMs, or transformer models. On the other hand, I think what we learned last week is that if we had a selfie, then the type of model that might be more conducive to using it would be a GAN or a variational autoencoder. So we just show here a quick picture that essentially takes a string-based chemical or molecular molecule and encodes that into a one-hot encoding. So each atom essentially is represented by a 1. Otherwise, it's just a bunch of zeros. And some other different ways that we might represent chemical information and for input to a machine learning model is it could be in the form of a scalar or a fingerprint. So in the case of a fingerprint, it could be like a Morgan fingerprint, which we also, I think there was also a presentation about the prior week. And in the case of having like scalar or fingerprint information, Typical type of models that we might work with would be a random forest. That could be a logistic regression model, or possibly support vector machines. And the picture here is actually taken from a paper that we'll kind of talk about on the next slide. But basically what this, what they did is they had kind of a clever way of encoding some chemical information into, into a vector. So what they did is they had basically six, they had a six-sided molecule. And so then they kind of represented it here. In this case, it was steric information and Hammett constants. And they kind of had those two each for, for each of the atoms. Finally, if we were to represent molecular information, with nodes or the actual bonds, and we were interested in perhaps we might have variable sized input, then something that we might use is a graph neural network. So I guess what, as Niels was saying, what are some common issues that we might encounter when we're working with chemical features and machine learning models? Well, one thing that frequently comes up that we usually see here is that there's just a limited number of examples to work with. Another thing would be that there might be imbalance between the classes. In this case, the classes could be like reaction types, or could be actually molecule types. So what we might see is like underrepresentation of certain classes, or different kind of mixtures of positive or negative samples, which we could see in the case of like different classification problems. Another common problem is referred to as the curse of dimensionality. And that's really basically saying that the amount of data that's required to get kind of good results generally increases with the number of dimensions that we're working with. So if we have a limited number of examples, then but we have, let's say, many features, that can sometimes be an issue. So what we might try to do then is, because we have a fixed number of examples, we may say, well, how can we reduce the number of features or dimensions? And some common ways, of course, that all of you are more familiar with than I am, is to use chemical insight and intuition and incorporate prior domain knowledge. So what we thought we would do is provide some type of somewhat of a case study of an example where there was some feature selection that was used for a machine learning model. This particular case study is taken from a paper that was published by the Grzybalski group a few years ago. And essentially what they were trying to do was to do Diels-Alder reaction outcome prediction. And so they, kind of similar to what we see in a lot of situations, they had a limited number of examples as far as machine learning models goes, which was, around 6,000. But in spite of that, they achieved, pretty high accuracy, in the 90% range for the things that they were predicting. So, a natural question might be, well, how did they achieve such high accuracies? One thing that they did, which was interesting, was they treated the machine learning problem, which again was related to, reaction prediction. They treated it as a classification problem instead of a regression problem. So instead of trying to, predict a precise reaction yield outcome, was it 93.5 versus, 82.1? They converted it into a classification problem. So that kind of helped with the accuracy, but certainly it wasn't the main reason for their success. What the paper concludes is that one of the most important things for getting high accuracies was to incorporate prior domain knowledge into the feature selection. So, their view was to, provide some chemical insight about the reactions to the model. And in their case, they focused on, instead of looking at the entire chemical reaction, which could include, many atoms and bonds, they focused on the reaction core and the key substituents. Another thing that they did was, or another conclusion that they had was that, in their view, that it was more important to, select good descriptors and features than it was to actually, get the most complex machine learning model. So in their case, what they focused on were Hammett constants and steric characteristics. It might be a bit cut off here on the screen, but what they basically did was, the Hammett constants are kind of in blue. The Hammett plus the steric is in yellow. And interestingly, some of their, R&D stands for random. So what's kind of interesting is, just using kind of random input, they actually got some decent results in a couple different situations. So, of course, there's no substitute for chemical insight when selecting features, but when we're doing something like that, how might we, use machine learning to inform chemical intuition? So a low-cost way to do that is with a decision tree, and scikit-learn, for example, offers a prepackaged Python version with some easy-to-use commands, and decision trees are essentially linear models. So there's a nice clear map from inputs to outputs, which allows us to figure out kind of feature importance. And with feature importance, we can possibly narrow down the features that we want to provide to a machine learning model. So what we show here is something that Niels and I were working on. We started out with approximately 250 different descriptors, many of which were taken from RDKit, and we said, well, why don't we just look and see if we can figure out what the top 10 descriptors are for purposes of a decision tree, in terms of what is the decision tree actually focusing on to arrive at its decision. So in this case here, we kind of show the top 10, which was helpful in terms of narrowing down the descriptors that we might look at. So another thing that can come up in machine learning modeling with chemical features is that the actual molecules may vary in size. And typically, machine learning models like to accept fixed size information in the form of a vector or some other type, or a matrix. So here, just as an example, we show toluene with 7 atoms, molupunivar, which is actually, some of you may be familiar with. It's actually had, it showed good results, I think, against COVID. So in that case, it's got 24 atoms as opposed to 7. So a question might be, well, how would we input molecules of different length to a machine learning model that's expecting a fixed size input? So, so how might we do that? One approach would be to, just use a fixed molecule size. So, a lot of natural language processing models that we saw before, like a transformer possibly, or an LSTM, what they might do is just say, okay, you could have a molecule that's 100 or 150 or 80, but we're just gonna truncate the molecule and say we're only going to use something that's 50. or we're only going to use 75. So another approach would be to just focus on the reaction center. And typically the reaction center would be something of a fixed size. On the other hand, if we wanted to use variable size inputs, we could choose a different type of a model. So like a graph neural network or recurrent neural network models are enabled to accept fixed size inputs. I'm sorry, I meant variable size inputs. So yeah, with that is, I guess, concludes our presentation. Thank you for your time. If you have any questions, please let us know.
Thanks, Damien and Niels. Any questions?
Just getting distracted by a cat.
It is our new kitten who is, wow, not wanting me to pay attention or work.
All right. If there is no questions, then thank you very much, everybody, again. Have a wonderful holiday. And I see everybody in January.